Asymmetric algorithms, including Diffie-Hellman, use a public key and a private key. So Whitfield, Diffie, and Martin Hellman created Diffie-Hellman, which is the first asymmetric key agreement algorithm. It's an asymmetric algorithm that can be used to create a symmetric key pair. This kind of revolutionized the whole way in which asymmetric algorithms were used. When using Diffie-Hellman, two parties will negotiate a group to use, which will determine the strength of the symmetric key. Diffie-Hellman has a couple different groups. There's 25 different groups within Diffie-Hellman, numbered DH1 to DH25. And different groups have different uses and different strengths. For example, DH1 uses 768 bits, while DH5 uses 1,536 bits. So let's take an example here. John and Kenya want to communicate with a secure session, so they must first exchange public keys. Now, how are they going to do this? Well, using Diffie-Hellman, John would take his private key and combine it with Kenya's public key using Diffie-Hellman. The algorithm would then process both keys and create a symmetric key. So let's take a look at this visualized. We have John here who would combine the private key with Diffie-Hellman and Kenya's public key. Okay, so his private key and Kenya's public key with Diffie-Hellman to create a symmetric key. On the other side, Kenya would take John's public key and her private key, apply it to Diffie-Hellman to create a symmetric key as well. So using that public-private key pair, the two are able to create a session key or a symmetric key that can then be used for symmetric encryption. Very handy, and this does not require public key infrastructure to implement. Switching gears, another asymmetric algorithm is Rivest-Shamir-Adleman. RSA, as it's known, is named for its creators, Ron Rivest, Adi Shamir, and Leonard Adleman. It's an asymmetric encryption algorithm that uses the mathematical properties of prime numbers to provide authentication and encryption. It takes the factor of two large prime numbers, and that's very difficult to calculate, which makes RSA very secure. RSA can be used for digital signatures and can be used to encrypt other keys as well. One-way function within RSA can provide encryption and signature verification, while the inverse function can perform decryption and signature generation. RSA is widely used throughout the globe. It's very secure, mostly due to the fact that it's very difficult to factor in two prime numbers. There's a mathematical peculiarity about it that makes it very difficult to do. It takes a lot of processing power, and it's one of the reasons why RSA is so effective. RSA is incredibly time-consuming because of this large computation power required. So it's not recommended for large amounts of data, but it's ideal for smaller bits of data, like encrypting other encryption keys.